Okay, so get this. Imagine a robot that learns to walk completely on its own. Not in a simulation, but in the real world. And it doesn't take weeks or months, it takes just 2 hours. Today, we're diving into the incredible research that actually made this happen.
This little guy is called Minitaur, and what you're looking at right here, this isn't some pre-programmed remote-controlled routine. Nope, this robot is figuring out how to get over a pile of junk it has never seen before using a walk that it learned entirely by itself. So yeah, that's the million-dollar question, isn't it? How on earth can a physical robot learn a skill this complex, this fast, and be this good at it? Well, the answer lies in a totally new way of thinking about how machines learn.
To really appreciate just how big a deal this is, we first have to understand why getting a robot to walk is one of the hardest problems in all of engineering. I mean, people have been wrestling with this for decades.
Just think about it for a second. Every single step you take involves this incredible symphony of balance, timing, and tiny adjustments to whatever surface you're on. For years and years, getting a robot to do that reliably has meant a ton of painstaking manual work from human engineers. The old way of doing it is what they call a pipeline. It's this long, complicated chain of commands. You have engineers trying to perfectly calculate the robot's position, schedule every footstep, plan the trajectory. It's a huge list. And the crazy part? The whole thing is incredibly brittle. If your physics model is off by just a tiny bit, the whole system can just fall apart.
But what if you could just skip all of that? What if, instead of programming every last detail, the robot could just figure it out on its own? This is where this really powerful AI idea called reinforcement learning comes into the picture.
The difference between the two approaches is really night and day. Traditional programming is like handing the robot a super detailed, step-by-step instruction manual for walking. But reinforcement learning, that's more like watching a baby learn to walk. It tries something, it falls over, that's negative feedback. Then it tries something else, manages a step. Hey, that's a positive reward. Through tons and tons of trial and error, it literally discovers how to walk all by itself. But there's a massive catch. This trial and error thing works great in a computer simulation, where you can run a billion trials in an afternoon. But trying it with a real physical robot, it's been practically impossible. The AI needs a ridiculous number of attempts to learn anything, which would take forever, and you'd probably just destroy the robot in the process. Plus, it's super sensitive to all of its starting settings. And this is where the researchers had their big aha moment. They decided to focus on one single crucial setting, a setting that basically controls the robot's sense of curiosity. The technique has a fancy name, maximum entropy reinforcement learning, but the idea behind it is actually pretty brilliant. The AI isn't just trying to do one thing, like move forward. It's actually trying to do two things at once: get the reward and be as random and exploratory as possible. This basically encourages it to be curious, to try weird things, instead of just getting stuck on the very first thing that kind of works. And this balance between getting the job done and messing around is controlled by something called the temperature parameter. Honestly, the best way to think of it is as the AI's curiosity knob. You crank it up, the AI gets more random and tries all sorts of new stuff. You turn it down, and it just focuses on the goal. Now, for years, the problem was that finding the right setting for this curiosity knob was a complete and utter nightmare. Some poor engineer had to just guess a value, let the robot run around for a few hours, see if anything happened, and if not, well, they'd have to make a new guess and start the whole painful process all over again. So what was the game changer? They created an algorithm that takes the human completely out of that loop. It tunes the curiosity knob all by itself, while it's learning. So the AI isn't just learning how to walk, it's also learning how curious it needs to be to learn in the best way possible. All right, so with this new self-tuning algorithm ready to go, it was time for the moment of truth. Could they really take a physical robot from a dead stop and teach it to walk quickly and efficiently in the real world? So here's the setup. The Minitaur robot is on the floor, collecting data as it tries to move. All that information gets sent wirelessly to a big computer, that's the brain. The brain crunches the numbers, updates the walking strategy, and sends a new, slightly smarter plan back to the robot. And that loop just repeats over and over and over again. And the result? It's kind of mind-blowing. In just 2 hours of real-world time, the robot went from just flailing around on the floor to having a stable, effective walk. 2 hours. That is a massive, massive improvement. And you can literally see the learning happen in real time.
At first, its movements are just jerky and uncoordinated. That's the AI just trying to figure out the basics, like, okay, what do these legs even do? How does physics work?
But then you start to see it click. A rhythm emerges, a coordinated, confident walk. The AI discovered that pattern. Nobody programmed it in. It found a solution all on its own.
But wait, the story actually gets even better. Because the most amazing part wasn't just that it learned to walk, but how it learned to walk. Because the AI was encouraged to be curious, to try all kinds of different movements, the final walk it learned was incredibly robust. This wasn't some one-trick pony that could only walk on a perfect, flat lab floor. Now get this, the robot was only ever trained on flat ground. That's it. So the researchers threw it a curveball. They put it on a slope, a situation it had never seen before in its life, and it just handled it. No problem. The skill had generalized. Then they pushed it even harder. They threw a bunch of wooden blocks in its path. And again, with zero specific training for this exact scenario, the robot just powered right through them. This is exactly the kind of real-world robustness that engineers have been trying to build by hand for decades. So why does all this matter? Well, it's a huge landmark. It shows us there's a real path toward building robots that don't need to be spoon-fed every single little instruction. Instead, they can actually go out and learn complex skills for themselves in the real, messy, unpredictable world. This really does feel like a giant leap toward a future of truly autonomous machines. And it leaves us with a pretty exciting question to chew on. If a robot can learn to walk in just 2 hours, what on earth is it going to learn to do tomorrow?